So, how was the question on the matching network in the quiz on the midsum? Got that one? So that no? Okay. So since we were discussing matching before we stopped before the end, maybe we can start from there. So let's take that question into account. I'll show you if it comes in an exam, how would I have gone about doing it? And when you are designing anything, how would you like to think about doing it, right? So those two are not necessarily the same things, as you might have already understood by doing projects and writing exams. So the question, if I recall, was this. You had a resistor and a capacitor, and you were asked to put something inside the box so that the resistance looking here was 4 times that of R, right? Or some multiplying factor of that of R at some particular frequency, right? Not across all frequencies. And the constraint was, in this box, you can put either R or an L or LC, right? But only one element, okay? So if somebody asks me this, then obviously the first thing I'll do is looks like a multiple choice, right? I can only put R or L or a C. So let me see, right? So can I put an R? Obviously, R will not make any sense because ultimately I have to, even if I put a R, the component, if I look from this port, right? So let's say this is one dash. So if I look from this port, I'll basically get some value of the capacitance, which will have an imaginary term, right? So that's not a constraint. I mean, that will not suffice. So R is out of the window, right? Can I put a capacitor? Obviously, same thing, right? You cannot nullify a capacitor with another effect of a capacitor with another capacitor. That also goes out of the window. So basically, the only thing that I can have is an inductor. Now, I have told you only one element, which means there are only two ways of connecting in this case. Either you connect it like this, or maybe you connect it like this. These are the only two options, right? So let's check the option which is the red guy, right? Series option. So if I connect it like this, note that you'll have to resonate out the capacitor. If we resonate out the capacitor, the combination of L and C gives you how much impedance? 0. So looking from port 1 and 1 dash, you get resistance of R. So that also goes out of the window. So what is the only thing left? Parallel, right? So now I have nailed down the topology. Now I'll do an analysis, right? So if that is the case, so let's do the analysis. So what I'll do, I'll apply a V-test. And then find out I-test, the same old, same old. So in other words, what I'm essentially saying is I'm trying to find out the impedance looking here, right? And then trying to find out whether the real part of the impedance is equal to 4R. And I'm hoping that this L and C combination will be such that the imaginary part will get cancelled out at some frequency, right? I don't know, that's the hope. So I don't have to apply V-test. I basically know that this is a simple RLC circuit. So I'll simply find the Y. Why am I finding the Y? Because looks like more things are in parallel than otherwise. If I do Z, then the math becomes slightly more complicated. So I'll simply find the Y. So Y is essentially 1 by j omega L plus the C and R in series in Y domain is essentially that the same expression that you have in parallel. So basically, it becomes j omega C by 1 plus j omega RC. So now you basically do a bunch of math. So this, I'll club these terms together. So denominator becomes j omega L minus omega square R LC. This is 1 minus omega square LC, right? I don't need to carry that j omega L everywhere, right? So I can simplify my life. So I'll just keep this j omega L as is. Denominator, I multiply both sides by the conjugate of 1 plus j omega RC. So this becomes 1 plus omega square R square C square. And this is 1 minus j omega RC. So in the numerator, what do I get? So the real term is 1 minus omega square LC. And this gets multiplied with that. So I get plus omega square R square C square, right? Plus J times omega RC. And what else? That gets multiplied there, right? Yes. So minus omega RC times 1 minus omega square LC. Is that correct, right? I'm not missing any term. Okay. So clearly here one term cancels, right? This one goes. So I end up with 1 minus omega square LC plus omega square R square C squared by j omega L square. And it becomes plus j times omega square LC by j omega L. Right, so we have this to be, this becomes the real term, the other one becomes the imaginary term. If I concentrate on the real term, what do I get? So this is the real, and this is the imaginary. In the real term, what do I get? So real term becomes real of y becomes omega square LC by omega L, 1 plus omega square R square C square. So basically cancel out this. This I expect to be what? So let me also This is omega c by 1 plus omega square c square. So this I expect to be whatever 1 by 4r, right? Because G was supposed to be more, so this is supposed to be 1 by 4r. So what do I get? 4r essentially 1 by omega c plus omega square r squared c squared by omega c, right? So which essentially means that you, okay, so let me also write it in a more clear fashion. Did I make a mistake somewhere here? Okay, let's concentrate on the imaginary part also. So imagine, so ideally this imaginary part, I think I made a mistake somewhere. So plus g omega c by g omega 1 plus g omega c is fine. So this 1 minus goes there, that goes here. Imagine. So okay, so far so good. Okay, fine. So your imaginary term is essentially is equal to this one 1 minus omega square LC plus omega square r square c square by omega L by 1 plus omega square r square c square, right? So this becomes 1 minus omega square LC plus omega square r square c square by omega L 1 plus omega square r square c square. Okay, so essentially what you have to do is to ensure that you have to size your device, size your that inductor L such that this goes to 0, right? So which essentially means that your LC is approximately, not approximately, LC is equal to 1 plus omega square r square c square by omega square, which essentially is 1 over omega square plus r square c square, or in other words, your L is 1 over c times 1 over omega. So let me write it this way. 1 over omega square c plus r square c, right? So this becomes the value of the L. And once you put that value of the L here, L doesn't exist here. Okay, fine. So once you, so basically all you have to do is to, for the particular omega, you'll have to size it in such a way that this goes to 4R, right? So, so the question is, yes.
So what variables in this circuit are fixed? Like omega naught is fixed, like omega is fixed to omega naught and R is fixed. And we can size C and L, or is it something?
Yeah, so the only thing was you'll have to ensure that this looking in impedance. So you have to, I don't remember exactly the wording of the question, but if I remember, it was like this was given at some particular omega naught. At some particular omega naught, what do you put inside the box to get 4R?
Since R and omega are fixed.
Yeah, right. So let's see if the R and omega are fixed, correct?
Can change again.
Yes. Yeah, correct. Yeah, right. So that's correct. So yeah, so if I do not know anything about matching and all, I know only basic circuit theory. This is how I'm going to go about doing it. Now, some intuitions that can come out of I'll spend more time on the intuition part, but at least from here, it's if you think, I mean, if I assume that, let's see what the circuit reduces to if I make some approximations, right? So if I assume that I can neglect this term, if I can neglect this term with respect to omega 1 over omega square, right? So in other words, I'm saying so if RC is much less than 1 over omega, i.e. 1 over omega RC is much greater than 1, right? So if this is the case, your resonant frequency is essentially 1 over LC, under root 1 over LC, right? That is the situation which we expect, right, if R is not there, right? So if that is also the case, I can basically then, I mean, I can obviously massage this equation for R to get something out of it. But the key thing that I would like to focus on here is for you to understand, in order to get, if I make that approximation of 1 over omega RC is much greater than 1, what I'm essentially saying is that the impedance of this guy is more than R, right? So if you think about this way, all I'm saying is that 1 over omega psi is much greater than R, right? So impedance of the capacitor is more than that of the resistor at whatever frequency we are looking at. Now, if you recall, we in the class before the midsem, we used that philosophy to come up with impedance transformation, right? So what was the philosophy? The philosophy was, if I have a lossless network and we have a R here, and I apply a voltage V in, and I see the current is I in, and based on the lossless network, I see this voltage is V in by N, right? I don't know how, but based on this by virtue of putting this lossless network, I am getting V in over N, which means the current through this is V in over NR. And we basically equate the power between the input and the output port. So we got, after we did that, we got V in times I in is equal to V in squared by N squared R, which means your V in over I in is N squared R, right? So you recall this we did just before the midsem, which essentially means that what is this telling us? It is basically telling us, if we are able to step down the voltage at the other port by the use of a lossless network, I'll mimic it. It almost seems like I'm mimicking a transformer of trans ratio N, right? So I'm able to step up the resistor by an equivalent amount. Okay, so this effectively, I mean, this effectively means this is like a transformer of trans ratio N:1 rather. So then this becomes N squared R, right? So using this philosophy, we did the analysis for an LR circuit. The one that I gave in the midsem was CR circuit, right? Exactly the same thing, the CR. So let's do that using that philosophy, because that philosophy will help in design. This writing one-page equation doesn't really help in design. So now what is the philosophy? The philosophy is, when I'm looking in from here, right? Or rather, if I apply some voltage here, let's say I apply V1 here and I get V2 here. What is the first principle? If I want to ensure that the R seems to be a magnified R at the other port, what is the first thing they have to do? Or what is the first thing that I have to ensure rather? The voltage V1 is stepped down on R, right? So what is the factor by which it gets stepped down in this case? So V2 is approximately equal to V1 times J omega RC, right? Or rather, if I write it in this way, Vy V1 times R by R plus 1 by J omega C, right? So if the step down has to happen, then the impedance offered by the capacitor has to be much more than the impedance offered by R, right? So I can basically neglect the R term in the denominator, and this approximately becomes, this is equal to, this approximately becomes V1 times J omega RC. Now this voltage, this is, I mean, even though you have a J in the term, it doesn't mean that the power dissipated in R is 0. This J is with respect to the phase of the input, right? So this, so the power dissipated in the R is still V squared over R, right? So the power, so P out is still omega square R squared C squared over R. Okay. So I'm keeping it in this format. So your P in, so if this is the case, your P in, sorry, this times V1 square, correct? So this is equal to, because there is, I mean, if I assume this is my network, so this is equal to V1 times I1. Correct? So I am equating real power here, right? So you'll have real quantities. So real quantity of I1, you can assume, because V1 is real. Okay. So essentially then your V1 over I1 becomes R by omega square, R square, C square. Correct? So all you have to ensure is omega square, R square, C square, in this case is equal to 1 over 4. I mean, if I take the example of the midsem, right? So if there is another generic term for omega 1 over omega square R square C square, that is called Q. So I will explain Q later on, but I can say that this is equal to R times Q square. Okay, so Q is equal to 1 by omega RC. So I'll come back to what Q means later on. Well, let's go with the fact that this is called Q. So now, so this is obviously when I equate power, I am only concentrating on the real power, right? So this is power dissipated, right? Power dissipated in one port, power entering the other port. I'm not talking about the reactive power, the stored power. That is not a part of this calculation. Fine. So it looks like I have a framework, but this will simply not suffice, because I'll have an imaginary component because of C. Correct? So at least I know that right now the real part of the impedance, right? Real part of the impedance, or if I say Z in, so some real part of Z in is equal to R times Q square, right? What is the imaginary part of Z in? Now note that we are working under the condition that the impedance of the capacitor is much more than the resistor. So what is the imaginary part of Z in approximately? One by J omega C, right? 1 by J omega C. So I have the real and the imaginary. Well, I should not say Z in, I should simply say impedance. because I don't know whether it's Z. I mean, right now I don't know whether these guys are in series or parallel. So I've got some real part, I've got some imaginary part. There are only two possible options. These two are in series or these two are in parallel, right? So what I'm essentially saying is, by the way, these are all approximations, because I mean, I'm neglecting the value of R with respect to 1 over j omega c. This is kind of approximation. So what I am essentially saying is, this approximates to either one of this or this. Right? C remains C, the R becomes R times Q square. How do I know which one does it approximate to? So for this case, you can probably make some corner cases, right? By the way, this is essentially R times Q squared is equal to, if I write it in terms of the actual expression, this is R by omega square R squared C squared, right? This is R by omega square R squared C squared. Okay, so let's assume your R is 0, right? So in this so we are working under the assumption that the impedance of the capacitor is much more than impedance of the resistor. So the worst corner case for that is R equal to 0. If R equal to 0, our model should be validated, right? So if R equal to 0, what do you see is happening here? What is the impedance looking in? 1 over j omega c. Sorry, no. If R equal to 0, what is the impedance looking in? Note that this guy goes to what? Infinite, right? So if R equal to 0, the impedance looking in becomes infinite. In this case, if R equal to 0, 1 over j omega c. So which one do you think is a more accurate approximation? The series or the parallel one? The parallel one, right? So I can basically say that so this guy approximates to R times Q squared times C, right? Not exactly equivalent to, approximately equal to, under the condition that 1 by omega RC is much greater than 1, right? So if that is the case, now I have this 2-port, which I have reduced to this form, which has a capacitor attached to it. So what should I do now? I have to get rid of the imaginary part. So basically this is this, right? So this is 1 dash, this is 1 dash. I have to get rid of the imaginary part. What do I need to do? Connect an inductor here. So basically I need to connect an inductor here, which is equivalent to connect an inductor of the value which is equal to 1 over, such that omega square is equal to 1 over LC, right? So this is the intuitive way of going about designing this. Okay. If you have done either of them, fine, no issues, right? But when you are designing, obviously you see that it makes more sense to think about this in this intuitive way, because it kind of gives an idea of how a transformer works, and you are relating your concepts to the working of a transformer, right? And that's what a step down of a voltage or a step up of a resistance looks like. Basically transforming an impedance. So think in terms of how the voltage or the current goes up or goes down. Okay. Any questions so far? Yes.
But the quality factor there should be 2, and it moves approximation. I think it's not enough to do this approximation.
So ideally it comes as, this R comes out to be, if you do the exact calculation, if you plug in there, it becomes 1 Q square plus 1. it will come out to be, if you do the exact analysis and plug the values there in the original equation, you are going to get R times Q squared plus 1. That's okay. I mean, you do this or that, I'm okay. Because the whole idea of doing this exercise is we know that a simulator exists, right? We are going to get a first order design ready with our calculations, then we'll put it in the simulator and let the simulator do, and I'll tweak. Right? So that anyway is the goal. Right? So as long as we understand where the design is headed towards, we're okay. So obviously, exact analysis will always give you a more exact answer. That's not a surprise. Okay, fine. So now, once you know this principle, the reason this principle of stepping down and stepping up is important, because once you know this principle, you can come up with n number of matching networks. Because all you need to do is to find out a way of voltage dividing, or rather, I mean, stepping down a voltage with the help of the lossless network, right? So, for example, so what all things did we do till now? We essentially did this. Sketching the imaginary part resonating off in red. So looking in here, so this is essentially equal to U squared R LC, where what is the value of R? What is basic? Forget about Q squared R. So what is the step down? What is the step down ratio by which your R is getting amplified? Pardon? No, in terms of omega L, R, C. Yeah, right. So step down is happening because of this. Right? So basically your Q is essentially omega L by R. Right? So similarly, I can do. So by the way, I mean, here in this case, this works. This circuit works under the case that omega L is much greater than R. This circuit works under the case of 1 over omega C is much greater than R, or rather the omega C is much less than 1 over R. Right? So this gives the circuit on the top works under the assumption that the frequency is lower than something. And the circuit on the bottom works under the assumption that the frequency range is higher than something. Right? So now naturally, based on your design requirement, you can choose which one, because the frequency will be given to you. Very often in RF design, frequency is not a free variable, right? It's given to you. All you can play around with and often R is also given to you because you are transforming that R to something else, right? If you could have changed R, why did you need a matching network? So omega and R are given to you. So all you have to do is play around with the component values. In one case, it seems like it is true for a lower value of omega, right? There is an upper limit. In another case, looks like there is a lower limit of omega, right? But this is only limited to these matching networks. You can come up with several other matching networks where these constraints are not there. For example, I want to use a step down using capacitor, but not have the constraint of lower value of omega, right? So I can basically then say that all I'm saying is I need to step. So by the way, why is this lower value of omega constraint coming in this network? I want high impedance here, right? So if I do not want that constraint, then I have to put some capacitive network here so that the impedance looking here for the capacitive network is much lower than the R. Right? I want to get rid of that constraint of capacitor imposes a higher limit. Then I have to ensure that the step down happens independent of R in some way, right? So now, right now, the R is a factor of R is playing a role in the step down ratio. right? If I do not want R to play, I mean, if I want to make the step down ratio independent of let's say omega, right? So then I have to get I have to design some network so that the step down ratio is not dependent on R. So what is the easiest way of stepping down any voltage? Consider resistive divider, but obviously I cannot use a resistive divider there because it will be dissipative. What else? Some other resistive divider. What other resistive dividers can you think of? You have RLC. Capacitive divider, right? So you can have a capacitive divider. So basically say, you can have a capacitive divider, C1 and C2. And this is my V1, right? So this voltage V2, I'm approximating as capacitive division ratio, that is C1 by C1 plus C2 times V1. This division is applicable under what condition? Because clearly this is not true always, right? Because R should be a part of this division ratio. Yeah, so this is true only when the impedance of Thevenin impedance of this capacitive divider is much lesser than R, right? So this is true only when this is valid only when 1 over C equivalent, omega C equivalent is much lesser than R, or in other words, omega C equivalent is much greater than 1 over R. So you get another constraint, right? Which is not limited by the lower frequency of R, it's limited by, higher frequency of omega, it's limited by the lower frequency of omega, right? So without getting into the again math of it, now you know, right? So this effectively looks like a turns ratio, right? So or rather, if I say, express it like this one becomes V1 times 1 plus C2 over C1. And I say this is to be equal to, let's say, Q. I shouldn't say Q in this case because not, so I'll just say this is equal to N, right? So effectively, this should behave like a transformer, which is N is to 1, where N is 1 plus C2 by C1. Right? So this is not yet ready because this is only the real part. I have to resonate out the imaginary part. So how can I resonate out the imaginary part? This is simple here because we are anyway saying that the impedance of C1 and C2 is dominating. So effectively looking from port 1 also, the impedance of C1 and C2 will dominate. So I have to put an R, I have to put an L, which will resonate out series combination of C1 and C2. So essentially, this L should be such that, so omega square L times C1 C2 by C1 plus C2 is equal to 1. Right? So, and you are done. Right? So now you can see, now you see that you just express your interest in English. Right? You set up the network in such a way it divides the voltage and you resonate out the imaginary component, and you have a matching network of stepping up the equivalent resistance. Correct? So now, when any questions, any confusion? Okay. So now we are concentrating till now only on stepping up a resistance. You can also do naturally stepping down a resistance, right? So while trying to step up a resistance, what were we doing? We are essentially trying to reduce the voltage, right? We are stepping down the voltage at port 2. That leads to step up of the resistance in port 1, right? So now if I want to step down the resistance at port 1, what should I concentrate on port 2? Step up is difficult to implement, right? So I would like to change the variable of interest, and I'll basically say, I would like to step down the current. Right? So if I have to step down, so basically if I have to step down a resistance in port 1, I'll try to step down the current in port 2. Right? Does that make sense? So, I mean, if you are not convinced, you can basically, again, go back to this guy, right? Instead of expressing, okay, let me sketch it separately instead of going back and forth. Again, this is lossless. And if I want to step down a current, my main variable of interest of the input port, I say is I in. And let's say the current through this is I in over N. Right? So the P out is I in squared by N squared times R, right? I square R, which is equal to I in times V in, or I shouldn't say in, I should say 1, right? Because that's what we are repeatedly saying, I1, 1. I1 squared V1. In other words, your V1 over I1 times V1. In other words, V1 times I1 is equal to R over N squared. Right? So you start your thought process from assuming that you want to step down the effective current going into port 2. Right? So now tell me a circuit that can do that. So I have R. I have to put something here. Forget about the resonating part. Resonating part we'll think about later. What can I put here so that if I put in a current source I1, the current through this will be a fraction of I1 at some frequency omega, obviously not a DC. A capacitor in parallel, right? So anything in parallel will reduce the current through R. I mean, that's trivial. And I don't want to put a resistor and to put a capacitor. I can put a capacitor. I can even put an inductor. Right? So let's stick to a capacitor. So I put a capacitor here. So what will be the fraction of current going into R? So this I2 will be I1 times what? The conductance ratio, right? G upon G plus J omega C, right? And you want, let's say you want the step down to be decent fraction, right? Large fraction. What can you neglect? You can neglect G. So this becomes I1 by J omega RC, right? So your step down fraction is how much? Your N is now 1 over omega RC, right? So this will take care of the real part, but I still have an imaginary part available. So how do I resonate out the imaginary part? I have to put an inductor, but in series or in parallel? If I put it in parallel at resonance, what is the current through R? Is I1. It's not stepping down. So I have to put it in series. Right? So the hack to remember this is current and voltages are dual. So if you do something with a voltage and you want to do the same thing with a current, all you have to do is change the capacitor to an inductor, inductor to a capacitor, series to parallel, parallel to series, and R to G. If you know one, you can blindly do the other. Right? So that's the math way of doing about it, but the intuitive way of doing about it is this. Okay. So if you do this, so you are going to get a step up in the resistance. Step down in the resistance, right? So it should not surprise you because if you think about it, the step step up in the resistance was what? Was this, right? So we had this. So looking in from here, we had step up of the resistance, correct? So in other words, I can say that if the impedance looking here is R low, I am getting some high impedance looking here, right? So the other way of saying is, if I look from here and I look from here, then the R high seems to get translated to R low, isn't it? And that's what we are doing here, right? In the top, you're basically changing the port, where I am applying and where I am observing. So if the impedance transform, just like a transformer, you can look from this port or that port. The impedance either goes up or goes down depending upon which port you are looking at. So it's not surprising that if something is acting like a transformer, looking from one port, I should get the same, I mean, inverse of that looking for the other port, right? So even without going into current division, if I know how to voltage divide, I can basically flip the ports and look at it from that angle. Okay. Any questions?
Example that you said before.
Yeah.
Capacitor divided.
Yeah.
There is input R on the top and V
Yeah.
on the bottom.
Yes. So you can basically what is pointing out, you can flip the same thing here also in this capacitor divider thing. Right? Just like looking into V1, it seems like you have larger impedance. If you attach an impedance, if you attach a resistance at V1 and look from V2, you should be able to get a lower impedance, right? So anything that you are able to make a transformer with, you can flip the ports and you should be able to get the inverse relationship, right? Any questions? The reason I love this type of explanations is because, see, when you are doing a design, you don't have the time to or the mental bandwidth to write one page of algebra. And you can write something, and then if it doesn't work, then you are too tired to come up with another circuit, right? So, but if you know, it's like a Swiss Army knife, right? So you can use it for any way you want, right? You want to step up, you step up. All you need to know is very basic things that you either step up a voltage or step down a voltage, or rather step down a voltage or step down in current. If you know how a transformer works, basically use the philosophy and resonate out the imaginary part. By the way, it goes without saying, all these things work for very narrow band frequencies, because when you are resonating something out, it only works ideally for one frequency range, one particular frequency. It's not a broadband solution. And even the bandwidth of the system, that is around, if you are able to resonate it out around, let's say omega naught, then around omega naught, some range of frequency, this approximately is going to work. But if you go to like twice omega naught, it's not going to work. Right, so that's an inherent assumption, but that's true because all our RF systems which we are using are mostly narrowband. So this kind of narrowband transformers are fine. Okay. Any questions so far? Okay, fine. So now, once we have this framework, you should be convinced that now no resistance is small enough or no resistance is large enough to implement matching, right? So RF systems at the input port requires matching. If I see some resistance, I can and which is lower than 50, I can step it up. If I see something which is higher than 50, I can step it down. I have a matching network to play with. So we are going to basically use these types of matching network without thinking twice about it in the later courses, in the later lectures, as and when required. But there is a caveat. The caveat is we have completely disregarded the non-idealities associated with a matching network. For example, there is always a resistor associated with a inductor. There's a resistor associated with a capacitor, which means there is a loss associated with them. right? We completely neglected that. So the next part of the lecture is basically to concentrate and see what is the effect of those losses and how can I model it. And therein you will see the effect of Q factor coming in. The Q that I have been talking about without really explaining much, that part will come in now. So the definition, the classical definition of a Q is if you have a network, any network, with RLC or whatever, I mean, you can, any linear network, right? So which has RLC, you can have control sources, it doesn't matter, linear network. Then Q by definition is energy stored per cycle by energy dissipated per cycle. Or in other words, power stored by power dissipated. The slightly nuanced is supposed to be maximum power stored by power dissipated. But I mean, for our case, we'll stick to power stored over power dissipated, right? So if you do phasor, it doesn't really matter. So if you have I mean, very simplistic way, if I have a inductor with a resistance associated with it, RS is a series resistance associated with the inductor, because inductor is ultimately a piece of metal. And in an IC, the metal resistances are not particularly as low as you get in an off-chip interface. So in an IC, almost invariably, the losses of passives are dominated by that of inductor. But we'll do both, the capacitor and the inductor both, right? So if this is the case, and this is your stuff inside the box, what will be your Q? Q essentially is power stored divided by power dissipated. And what is power? Power, if I put in a current source, power dissipated is I squared times the real part of the impedance that I see. Power stored is I squared times the imaginary part of the impedance that I see, right? So power dissipated is I squared. So this is in phasor domain, right? Obviously, I squared times real Z in, and P stored is I squared times imaginary Z in. So you'll see that I am going to use I and V depending upon which math is easy, right? You can do either, but I would like to make my life simpler. So I'm just in this case, because they are in series, I'm putting a current source. If they're in parallel, I'll put a voltage source. Okay. So this Q is essentially, what is the real part of the impedance? RS. What is the imaginary part of the impedance? Omega L. So Q is basically omega L by RS, right? So this is often called the component Q, because I'm talking about the Q of one inductor, right? So this is called QC, component Q. Okay. If it's a network Q, we simply call it Q. Okay. And it need not necessarily be that network Q is equal to the component Q. That makes sense, because I'm only talking about only one component. If I have multiple components, the energy stored and energy dissipated relation might change, so effectively Q can change, right? So similarly, if I have this scenario, a capacitor and a resistor in parallel, so to make my life simpler, I will just put a voltage source, because easy to deal with. So in this case, your power dissipated is V squared times the conductance, effective real conductance, right? Real G, and power stored is V squared times imaginary. This is Y. So your QC will be what? Power dissipated is what is the real part of the conductance? 1 over R. So power dissipated is 1 over R. And what is the imaginary part of the conductance? Omega C. So this becomes omega RC. So this becomes the component Q of a capacitor with resistor in series, in parallel, right? But let's say I have a different configuration where I have this. So what will be the component Q now without writing out a bunch of equations? It will be 1 over omega RSC, right? Similarly, if you have this, what will be the component Q? Somebody else? Yes, Nivas. Why? Yeah. You are right, but I'm just explaining, requesting you to explain why. Okay, fine. So as long as you are convinced, I am also convinced. Okay, fine. So the reason I did these 4 configurations is when I was a student, it used to confuse me at times. Sometimes we are saying that Q is omega L by R. Sometimes I'm saying R by omega L. Sometimes I'm saying omega RC. Sometimes I'm saying 1 over omega RC. Right. So it's nothing magic. It's basically which configuration you are using. Right. So you have to be cognizant of that. Okay. Fine. So now, if we have a so now you might, another question that sometimes comes when we are doing RF for the first time is that why do I bother expressing in terms of everything Q? I know omega R, C, all these things I know, right? So why don't I keep everything in terms of omega R, C? Why do I have to say introduce another term, right? RF is a term heavy course that I told you at the beginning. So why do I need to put in another term? The reason we need to put in another term is even though it gives you the feel that everything is very controllable in the denominator omega RC, it's not, because omega is fixed, is set by the system. Then you might say that R and C I can choose, or R and L I can choose. L you can choose, but the R comes with the L. Right? Ideally, I want the R to be 0. I want lossless element. Right? But as it turns out, for certain value of L, if you choose, let's say 1 nanohenry of inductance, you kind of get 1 ohm or 2 ohm of resistance free with it. You cannot do anything about it. So which essentially means that in the denominator, you only have this L or C as a free variable. Everything else is fixed. Right? And since you cannot do anything about it, you as well go along reducing the number of things that you cannot change in your expression, right? You just club everything into Q and say, what is the Q factor of your element? For example, often you will hear that the Q of your inductor at 1 gigahertz is approximately 10 or 15, which essentially means that omega L over R is equal to 10 or 15 at 1 gig. If you know that information, you automatically know that at 2 gig, it's probably 20 or 30, right? Or at 10 gig, it's probably like 10 times of that, 200 or something like that, right? So naturally, you see that if you use an inductor with a series, which comes with a free series resistance, it is beneficial to use an inductor. A higher Q means more stored energy and less dissipative energy, right? It is better for a matching network to use an inductor at higher and higher frequency, because Q is increasing, or in other words, the stored energy is increasing. The dissipation in the network is reducing as a fraction of the stored energy, right? Similarly, when you are going at lower frequencies, and if you assume that series resistance with capacitor model, right? So in that case, obviously, the Q increases if you use a capacitor at lower frequencies. That's why you will see that as you go at higher and higher frequency RF, in RF design, you see more generous use of inductors because they are more efficient in terms of loss. And if you limit yourselves to a gigahertz, couple of kilohertz or so, when you see more use of capacitors. Okay, but again, this is a very hand-wavy statement. It's not as if you do not want either. Depending on case-by-case basis, you might see a different usage. But rule of thumb, if you are in the lower gigahertz regime of operation, you use the inductor to only resonate out the imaginary part of the component of your matching network. If you are very high frequencies, then you use capacitor to resonate out, and step up, step down is done by the inductor, right? Simply because they are more efficient. Okay, fine. There was something else that I wanted to focus on before I moved on here. Okay. So again, goes without saying, if I tell you the Q, right? If Q is known, and I say that your power dissipated is essential. So since I know that Q is power stored by power dissipated, if Q is known, then I can simply say that power stored is equal to Q times power dissipated. And this is generic for any, and vice versa. If I know the power stored, I can come to power dissipated, and vice versa, right? So that's why Q becomes very important fact. Just like noise figure conveys many things in one small term, a Q factor also conveys many things just by that term Q, right? It will convey how dissipative your network is. It becomes important in the next part of the topic. So essentially, from Q you can. Why we are interested in Q? Not only it goes step up, step down, it also gives you an understanding of how lossy your matching network is. Right? Ideally, you don't want it to be lossy, you want it to be lossless, but you cannot do away with it. Loss is a part of the system. So it should be able to give us an idea of how lossy your matching network is. Right? So let's say I have a matching network which has some Q. Network Q, not the component Q. I have a network Q. And I have P in, and this is P out, right? So if the matching network is not lossless, then the relationship between P in and P out is not that of equality. That is pretty intuitive. So your P in is essentially then power dissipated in the network plus P out, where P out, P dis is power dissipated in network. Okay. Fine. So I need to get an estimate of this power dissipated in terms of Q. That's the whole purpose of all this story. I will make another assumption. This matching network contains one L and one C. Right? Because that's what we have been typically doing, right? If I have multiple C's in series, I'll just combine them and say it's a one C, right? So that's, or multiple L's in series, we'll combine them in, let's say, one L. So basically, effectively, I can say it's one L and one C. Fine. So I have to basically then figure out what is this power dissipation, right? And I'll make another assumption that power dissipation in the network is mostly due to the loss in the inductor and not because of the capacitor. We are not working at like millimeter wave regime where capacitors are lossy. In this course, we are working in like gigahertz, couple of gigahertz range. So we'll assume that the loss is because of the inductor and not because of the capacitor, right? That's an assumption. So essentially then your power dissipation is equal to power loss in inductors, right? Which I can basically say is equal to the Q factor. So what is the relationship between power stored and power dissipation? Power dissipation is essentially power stored divided by the Q of the inductor, right? So this is basically equal to power stored by component Q, right? Q of the inductor. So this is component Q. Okay. Fine. Now I'm going to make a conceptual leap, and the leap is I'll just show you one resonant network. You can assume it's a parallel or a series, it shouldn't really matter. At resonance, if I see the voltage and the time and the current through these capacitors and inductors, so if this is the voltage and this is the current, so they are 90° out of phase anyway. I mean, not only at resonance, at any frequency they are 90° out of phase. But the total at resonance, the energy is okay. Before going to resonance, so the total energy stored in the tank is the magnetic energy in the inductor plus the electric energy in the capacitor, right? At resonance, they are identical. So they are exchanging equal energy of energy between each other. So they are identical, right? So it's neither blowing up nor blowing down. So they are identical. So in principle, then I can say that if I know the maximum current in the inductor in time domain, in maximum current, at that time the voltage across the capacitor is 0. Right? They are 90° out of phase. So the maxima of, I mean, dIdt, right? So if I have a current maxima, then I have a voltage minima. If I have a voltage maxima, I have a current minima, and so on, right? So if I have to then find out the total energy of the tank, I can basically then find out the maximum current in the inductor, and Li square is half Li square is the energy of the tank. Okay with that, right? So I can basically then say that in phasor domain, power stored is equal to power stored in the inductor. The power stored in network is equal to the power stored in the inductor. Correct? Fine. Fine. So essentially, then I can say your power dissipated is equal to power stored in network by QC. So in terms of the Q factor of the network, what is the power stored in the network? So now I'm making another assumption here. I'm assuming that the power loss in the network is negligible with respect to the power dissipated at the port 2, right? I mean, that's anyway that goal, right? If that is not met, then there's no point in making a matching network, right? So if I make an assumption that power delivered is much greater than the power dissipated in network, right? So now from the if I put a box here, the power delivered is essentially the power loss. You can think of power delivered as a power loss for this big box, right? Do you agree with that? So this R, the whole purpose of doing all these things is deliver power to R, right? I am to deliver exact power, whatever I am delivering from the input side to R. I can basically change the English language and say that the deliver is loss, right? As far as the red box is concerned, some power is going in, nothing is coming out. That's lost, right? So all I'm wanting to do is I want to put R inside the matching network and say that the Q factor of the network includes R. Is that clear? Okay, if that is not clear, think of it in this way. So all these matching networks that we have done, right? Let's take this example. What is this Q for this inductor R circuit? Omega L by R. That R is essentially the load, right? I am just put the, I mean, while defining Q, I took the load into account. So essentially, this is the load, this is the Q of the network, but the way I wrote it was essentially, it became a component Q. But now I'm making the distinction that inductor has some small resistance and we have a separate R. But while finding out the network Q, I am taking that load R into account. Does that make sense? Fine. So if that is the case, I can basically then say that power delivered is equal to Q times power loss. Power loss is essentially power dissipated. Correct? So now this dissipated is not, sorry, Q times power stored, right? Not power loss. It's the other way around. Yeah, right. Q power delivered is power stored by Q. But Q is the Q factor of the network. Okay. So fine. So now what were we? We essentially were power in is equal to power delivered plus power dissipated. Power delivered is power stored by Q. Sorry, I'll just keep it as power delivered plus power dissipated. Power dissipated is power stored by component Q. This is power stored by component Q. And power stored in terms of power delivered is, so this power stored is essentially Q times network Q times power delivered. So this becomes power delivered 1 plus Q by QC, right? So which means your power delivered is equal to power in by 1 plus Q by QC, right? So what is this telling you? It is basically telling you that if Q is essentially the network Q, again, QC you cannot do anything about it. It comes with the network, with your matching network component that you have chosen. Q also probably you cannot do much because omega is fixed. Resonant frequency ensures that the value of the component is also fixed, right? So all this is telling you is that if you choose a high Q network with a fixed loss, fixed QC, you are going to have lower power delivered, right? In other words, higher the ratio of Q over QC, higher the ratio of the network Q to the component Q, more the loss in the network. That should make sense intuitively because let's go to this example. In this case, forget about the inductor for the time being, okay? We used this ratio, we used the capacitor R combination to reduce the fraction of current that was going into R, which means most of the current was going into C. Now, if C is lossy and much of the current is going into C, then I will have more loss. Similarly, in this case, if bulk of the voltage is dropping across the inductor, which means the current through the inductor is also large, right? So we'll have more loss if the inductor also has a lossy element associated with it, right? Does that make sense? So good thing about, I mean, in principle, how is this impedance transformation happening? You are trying to store more and more energy, either in terms of voltage or current, into the matching network. Higher the Q, more the amount of energy that you are storing. And now, which means you can think of it like more amplitude of current in the inductors and capacitors, right? More amplitude of current and voltages into the inductors and capacitors. Now, if the inductors and capacitors also come with some lossy element, that increased amplitude of current is going to have increased amount of loss, right? So even though in principle, you seems like you will be able to transform any impedance to any impedance, which means that in principle, I should be able to have any Q. but it comes with a cost that if your Q factor requirement is large, if you want to transform a 5 ohm impedance to a 50 ohm impedance or a 1000 ohm impedance to a 50 ohm impedance, then your Q essentially, which is under root the ratio of the impedances effectively, that will determine the loss of the system, right? So like you must know by now in design, if something is too good to be true, it is probably not true, right? So this is one example that in principle, even though matching network seems to be this magic wand which you can use to transform anything to anything, it comes with some loss. And this typically is referred to as insertion loss. When you take up a data sheet of any RF system, you will see one plot of insertion loss. That insertion loss is basically will tell you how much loss you have in the network. Okay. In the next class, we'll see given certain amount of insertion loss, what you can do to optimize for the loss. I still want that ratio. What can you do to optimize the loss? Okay. Okay. Thank you.